Okay, good afternoon, everyone. So welcome to EC M16/CS51A. So I'm going to be the instructor for the quarter. This is my name up there, Manish Srivastava. I'm a professor in both electrical computer engineering and in computer science. And I've been teaching this course for quite some time. So let's see. So we are first going to go through some logistic type things and also want to take the opportunity to introduce the TAs and trading and stuff like that, all the good things that I'm sure you're very keen to know about. And then we'll have some introductory material. So let's dive in. Just give me a moment. Okay, so this is the information. So I'm part of my home at UCLA is really the computer engineering part of ECE department, and I work on sort of essentially computer systems that interact with the physical world in some manner. So as opposed to kind of servers and desktops and things like that, we kind of, my lab, my students work on sort of what's called as cyber physical systems or embedded computing systems, essentially things that interact with human beings, with physical systems, through sensors, do some processing, and then command and control them back. And in that context, we look at a variety of different issues, how to build these systems, the algorithms behind them, the design tools behind them, looking at some societal issues like security, privacy, those kind of aspects. My office is in this building, 3 floors up. My lab is also in this building, 3 floors down. If you enter from the southwest corner, right opposite the elevator, it's called Nestle Network Embedded Systems Lab. Sometimes if you have to meet me, you'll find me there. Let's see. So we have 2 TAs in this course. Julian de Gortari Brisno, he's my student actually, Julian. So actually, Julian, if you can stand up and just say hi. So Julian works in my lab, so obviously does the kind of things I'm describing. In particular, he's currently working on things like human-robot collaboration and also some security type issues and detecting complex events from sensors and all. This is his first time TAing. Actually, both of our TAs are first-time TAs. So that's Julian. Ji Cheng He is our second TA. He is not my student, but he's a student of one of my one of my colleagues, Professor Leha, and he works on, again, part of computer engineering, and he works on architectures for a certain kind of digital systems, which are called as field programmable gate arrays, as well as design tools on how to take algorithms and kind of map them to them. His work is actually very close to what, in a way, this course is about. So both our TAs come with a lot of experience in computer engineering. So even though it's first time around, I think you'll find them that they are really, really well qualified. I have posted our email addresses out there, but the best way to reach us really is through a note on Piazza. You can send a private note to the instructors, to a specific instructor, to all instructors. We are going to be very monitoring it and be responsive there. If you send us an email, in general, it's going to take a longer time. That's not where we primarily look for things. But just in case you do decide to email us, despite our advice against it, make sure to label the subject line as like ECE M16 or something like that. If you are one of the honor student, then ECE 89, in case the material is relevant to that. But again, I urge you to stick with Piazza. For a variety of reasons, but mostly because you'll find that our response time is much better there. And a lot of time, your questions may get answered by your peers. Okay, so our schedule. So lecture, obviously, you are out here. Yeah, there was already a question on Piazza. Will I be recording the lectures and stuff like that? And hopefully I am. Actually, let me just verify. I forgot, but yep, we are. Okay, yeah, I try to record the lectures, but again, I can't promise it. Often there are technical snafus. Last year, I was teaching in this room and we had huge amounts of AV problems there. So no promises, but I try to. And short of it having an impact in terms of very poor attendance, I don't want to stand in front of an empty room. I intend to keep doing it, but again, 2 things. Firstly, in case I decide to stop recording, it's not a valid ground to go to Dean and complain. Professor Srivastava said that he's going to record and he's not. I want to make it absolutely clear. I'm doing it purely on a voluntary basis. I say it because there was a complaint like that, which I felt was misplaced. So again, as long as attendance remains healthy, I intend to, but if I see that it's having a detrimental effect, I will stop doing it. I do believe that you'll find these lectures, even if you're attending, to be kind of useful. Let's see. It takes me usually a few days to kind of get, usually I do it on the weekend, so it's not like the recording could be there immediately. I do some editing and all before posting them. We have 4 discussion sections. So tomorrow's and the latter one on Friday are handled by Ji-Cheng, and Thursdays and the first one on Friday by Julian. Again in this building. And then office hours. So I and Julian are holding our office hours on Zoom. I kind of feel that Zoom office hours have worked out better. I'm able to sort of show things on whiteboard, go over the slides and all, and more students are able to participate. Ji-Cheng plans to do it in person in Engineering 4, the neighboring building. There's a TA room, so he would be there. Currently, you would see that we have coverage every day, and I think there are 2 office hours on Friday, which I think also works out well because most students seem to start doing their homeworks and all over the weekend. So Friday tends to be kind of a good time. During the weekend, we'll try to monitor Piazza, but just remember, we also have our personal lives, so the response time may not be that great, but generally we try to be responsive. Okay, let's see. So a little bit about the class. Half the class is EE students, and then another sort of half is basically split between CS students who I guess hate being in this class because it's too hardware oriented. My apologies. It's not my decision to force you to take hardware courses, but I know you all want to do machine learning. So so be it. Computer engineer CE degrees, there are CSE degrees, and then I guess a few students who want to move to CS, I guess. So anyway, so we have a mixed class. As you will realize that computer engineering at some level is about making computational systems, and whether you express that eventually into hardware or software or some mix of the two, it doesn't, much of that design process doesn't really matter. So hopefully, even if you are deep into software side, you'll find that a lot of what we talk about is useful. And likewise, those of you on the hardware side, you will realize that to be a good hardware designer, you need to be good at software. So they kind of go hand in hand, and hopefully you'll, as we go along, kind of see that. For many of you, I know a lot of students are freshmen, so this is kind of one of your first significant exposure to, I guess, a CSE type technical class. So if you see that you lack some of the background, like for example, I guess pretty much like any other engineering course, sort of we expect a lot of sort of background in terms of mathematical sophistication, even ability to program. I think we kind of take it for granted at this point. If you are struggling and all, reach out to our TAs, reach out to us. We can sort of point you to resources or otherwise attempt to help you out. Okay, so what's this course about? Title is Logic Design of Digital Systems, and there are really 2 phrases out here: logic design and digital systems. So I want to spend some time to kind of talk about what do we mean by that. Okay, so digital systems. So again, there are sort of 2 parts to it. What is a system? And system is a term engineers use a lot. In fact, many places, systems engineering is even a department. You'll actually, UCLA used to be like that until sometime in 70s. So essentially system, you can think of it like a black box of some form, which takes information as input and produces something out of that information as the output. Purpose could be as simple as learning about, let's say, the state of my body, and the output could be sort of deciding to intervene in some manner, maybe some drug or electrochemical stimulation or something like that. So by this definition, everything is a system. We are systems, right? I mean, we take sensory inputs from our world, and then we act upon it. We think, we make conscious choices and stuff like that. So engineers like to think in terms of systems because then we can develop a theory around how a system is behaving. If it's a closed kind of a system, then we try to understand it from its input-output behavior. In other cases, we are given a specification, and then we have to design our own system, right? And at some level, this course is more in the latter camp, which is given some specification, we wish to kind of do that. So then what's a digital system? So a system which takes its inputs and outputs in a digital form. So that begs the question, what does digital form mean? What does digital form mean? Anyone? Actually, what are some of the ways that you think information gets expressed? Can you be louder, please? Bits, bytes, binary. That's one example of digital information. The term digital comes from digits, discrete, right? So bits is certainly a way of doing digital systems. I guess commonly nowadays, when we say digital, we think bits, but it could be any form of a discrete thing would be digital. Bits can be expressed mechanically, chemically, you name it. And of course, our current systems, by and large, are electrical, right? We express digital values, discrete values in terms of voltages, usually just two levels, so that's 0 and 1, and most of the computers currently, most of the digital systems currently are designed like that. But if you kind of go back like even a century ago, things used to be electromechanical, with gears and relays and things like that. If you go back even further, the very first computers were entirely mechanical in nature. And then also there are chemical computers, people do DNA-based computing, almost any phenomenon where you can have discrete states, you can think of it as expressing digital information. Okay, so of course, what's the digital form? We kind of jumped the gun a little bit. Anything which can be represented as a finite set of values. Bits, which we'll spend much of the time in this course in some way, is really a discrete set where two value can be represented with 1 bit of information. So 1 bit, a set with two values. But what this finite set is, finite set of whatever discrete elements is, could be, I mean, at a mathematical level, it's just a finite set. Its physical manifestation could take many different forms, and we like to do it electrically in terms of voltages, but doesn't have to be voltage. What other electrical value do you think we can use to represent two values? Half the class is EE, so at least current. Yeah, exactly, right? Current. Now, for a variety of practical reasons, voltage is far more common than current, but you can certainly imagine creating digital circuits where two values of current, or current and no current, or current in one direction and the other direction could represent values. Okay, so what is not digital? Well, so at some level, when we think of digital information, there are really two parts to it: set of discrete values as opposed to continuous or real value, right? I mean, so like our heights are an example of something which is not digital, right? Humans come in all sort of height values. So it's a real number. Other things like air pressure or temperature, they're all kind of continuous. They're what we would call as analog values. There's also associated with digital is this notion that they are things that happen at discrete points in time. Just like I get whatever, let's say some information, let's say a bunch of values, and then at a later time again I get it, and little time I get it. Whereas a lot of real life things like temperature and all, they're continuous phenomena, they're continuous in time. So when we think of digital, there is really two types of discreteness that happens. We move from continuous time to instants of time, okay, and really nothing in between. And yeah, the other is that instead of real values at any particular time, we look at certain bins of values. So many of you I know are fairly advanced in E. So I'm sure you have heard of like things like sampling. I take a signal and I kind of sample at certain points in time. Maybe I sample it periodically. Does anyone know how do we decide how often to sample a waveform and still be able to recreate it? Yeah, okay, fine.
I think it's times the highest.
2 times the highest frequency. Excellent. So it's called the Nyquist rate. Okay, so it was almost just about a century ago that concept was discovered. Essentially, it says that if I take a analog signal, a waveform, I find its Fourier transform. Hopefully, you've encountered that in math. Yeah, look at the highest frequency component, and then if I sample at twice that rate, and if I know nothing else about the signal, right? I mean, if I just sample it, as in like, let's say the highest frequency is 100 hertz, right? So 2 times that is 200 hertz. That translates into 1/200 hertz, so a sampling rate. I sample the signal at that rate, and the theory says that if I know nothing else, right, other than the highest frequency, I can recreate the signal entirely, okay? Of course, if I know more about the signal, right, I mean, maybe I know something about the structure of the signal. Maybe you tell me that it's a combination of 5 sine waves or whatever, something like that. Then I can make use of that additional information to get away with a lower sample rate. But even if I know nothing else, just that information kind of suffices. So there's a whole body of work which deals with how do we go between these two worlds, analog to digital, digital to analog. So for our purposes in a digital system, even though most digital systems are designed to interface with the physical world, we kind of assume that people who specialize in analog to digital and digital to analog, they take care of that part, and we kind of assume that we have a purely digital input coming in, and I'm happy with a purely digital output going out. So if I'm, let's say, controlling steering wheel or speed of a car, designing a system for a autopilot system kind of thing, again, we don't worry about that final step of analog to digital, the hardware to do it, and what ramifications come from it not being continuous when we are spitting out the values. Kind of those theories are, let's say, well understood and outside the purview of this course. Okay, so what this course really is then about is how do we design digital systems? How do we not just hack our way through, but how do we design these things in a systematic manner? So what is a digital system, what is not? I guess at some level it's very hard because any system that we encounter nowadays has elements of both, in the sense that even if it's a digital system, deep down, it's interacting with the physical world. So on the right-hand side, I have a digital assistant. We call it literally digital assistant, right? But on the other hand, it interacts with us by hearing our voice and speaking back to us, right? And of course, the more modern ones are also sensing temperature, sensing your snoring, and sensing whether presence and absence of humans in the right. I mean, all these Google Assistant and Amazon Echo and these kind of things. So you would say the core is a digital system, but they're kind of really sort of wrapped in these kind of analog to digital, digital to analog. On the other hand, there are clearly examples of systems which are largely analog. Okay, a lot of the old stuff, right? I mean, our doors and things like that. I mean, they're kind of analog. But even they are changing. I mean, I think perhaps making things smart by putting home automation and these kind of things into the simplest of the objects is kind of what a lot of industry is currently about. So even things which, at least until now, have been largely analog, kind of are beginning to be quote smart, and therefore the core of it is digital. So can't escape either, really. Okay. So yeah, since we, as I kind of already alluded to, we are focused on designing digital systems, but they are sitting in a world which is essentially analog. By and large, there are bits of our natural world which are actually digital. Well, at a very philosophical level, physics is described in terms of quantum mechanics. So right there, you could say the reality is digital at sort of at a very fundamental level. Also, our brain operates in terms of firings of neurons, which are discrete events. So again, that's digital. Deep down in our brain, the timing of the brain is a clock tick. Again, it's discrete. So I guess really core level, a lot of world is discrete in time or discrete in value. But having said that, it then sort of expresses itself in terms of these values, which to us appear to be time, which is continuous, values which are continuous, and then we design our computers to sort of interact with it. So this part, as I already mentioned, is taken care of by these specialized hardware and the corresponding theories, which are about analog to digital conversion and digital to analog conversion. Analog to digital is where a lot of people spend a lot of time on, because doing it well is super important. And oftentimes, actually, in a system, this little piece, this piece is the one which sort of consumes a lot of power and things like that. Okay, so and also oftentimes signals are super tiny, right? I mean, the signal out here in many cases is like picoamp or picovolt and all, and you're trying to sort of get it out of the din of noise that also exists in the physical world. So it's not easy, but not something that we will spend a whole lot of time on, really. Okay, other than to say that there are these theories which guide us on how often should you sample, that's the time part, and how many bits you should have, and how do you assign those bits. So like, for example, kind of things that people who work on these things worry about are things like, you know, let's say I have a signal, let's say I'm measuring output of some analog sensor. That sensor, let's say, outputs values from 0 to 1 volt. And now how many, when I sample it, how fine a granularity should I sample it at? Because if I sample it very coarsely, let's say I sample it in just 4 bins, then I can, I'm making a lot of what is called as quantization error, right? Because I'm only able to measure 0.25 volt accuracy. On the other hand, if I divide it into, let's say, 1,000,000 bins, then I'm measuring it to 1 over whatever, 1e minus 6 volt. Okay, and maybe that's excessive. In some domains, signals are very tiny. In particularly, like if you're measuring, let's say you're measuring signals of brain activity from top of the skull, you're talking about very tiny signals. On the other hand, some other signals tend to be very sort of easy to measure. And likewise, digital to analog, this is usually when you are sort of commanding a motor or a artificial muscle or some light source or sound or these kind of things. And again, same kind of questions end up arriving out there. Sorry. Okay, so now examples of what are largely digital systems. So things like calculators and laptops and all, obviously, but even these things have analog outputs, right? I mean, if I look at my laptop, it controls the light level of the display. It can make sound. It has this touchpad, so it kind of measures that part also. It attempts to convey sort of analog information through the screen. So a lot of things, even in a computer like this, have an analog sort of flavor to it. But deep down, it's obviously mostly a digital system. There are some other examples out here. Are a lot of our systems like cars and all now have zillions of tiny computers in there. A modern car now would probably have 100, 200 processors networked together, controlling all aspects of the car, from your nav unit to brakes to engines and safety systems and whatnot. So some examples of kind of what I would call as kind of extreme edge of digital systems in recent years. So one which gets a lot of noise is, of course, autonomous vehicles. And I've just picked Tesla, but obviously there are many other vendors which are creating these things. We have Google's Waymo introducing their self-driving taxis here in LA, for example. So these things kind of depend upon computers which collect data about the immediate surrounding using sensors. Cameras is certainly one, but these cars also use other kind of sensors like LiDAR. Anyone knows what a LiDAR is? Heard of this one? LiDAR? Yeah. Go ahead. Yeah, so LiDAR shoots out laser beams, looks at the bounce, measures the time, gets the depth, and then it scans the laser beam. Actually, it has a curtain of laser beams. So like, imagine kind of like, let's say 100 laser beams stacked, and the whole curtain is moving, and it's kind of scanning, it gets a 3D depth map, okay? And then that coupled with what the camera is seeing, they kind of figure out where the car is. In fact, they pre-map cities in terms of this 3D scan in order to be able to do that. Radar is another thing that these cars use. That's a World War II era technology, but now we can buy radars really, really tiny and cheap, and they essentially work in the same manner, which is they send out radio waves, look at the return signal, and then try to make inferences about what is out there. Originally, this technology was for detecting incoming planes and missiles and stuff like that. And there are the other sensors like cars. Teslas use ultrasound sensors. Many cars still do. Your blind spot detectors, they usually work oftentimes with ultrasound, although often with cameras also. So now the point out here is these vehicles also have some pretty interesting computational power on board. In fact, I was reading someplace that some of these vehicles which are floating around, their brain, if you may, are burning 1.5 to 2 kilowatts. Okay, so it's you're talking about power consumption, which is a very significant fraction of the locomotion power. Okay, so normally we don't kind of worry about the latter. So this picture out here is the unit in Tesla, and it has two identical chips which process the sensor data and make decisions. Why do you think they have to? Yes, one fails. Yeah, redundancy. So cars are an example of redundancy. Of course, aircrafts and spaceships and military stuff and all are other examples. Oftentimes they use 3. 2 is kind of silly in a way, right? I mean, if the 2 are at odds, then what do you do? So I think if you're relying on some sort of a voting system, it's probably better to have 3. But here is probably more as a backup, which is one fails, then the other picks up the burden. Okay, this chip, I think now they introduced sort of another version just a few weeks ago, but my slide is a little bit older, but these are some of the biggest chips which are around. And what you see out here is they have graphic processing unit, right? I mean, this one, this partly is just for those pretty displays and all, which you see in the cars, but also to process the sensor signals using neural networks and all. You have neural processing units, which are dedicated to that. Neural processing units, which are dedicated to that. And then there is a classical CPU, a normal computer, which kind of exists out there. So these are what are referred to as system on chips. They are integrated circuits, the chips, right, which integrate multiple different things, which historically used to be separated out. Like, for example, in many PCs, GPUs are still those NVIDIA's GPU cards that you buy. But a lot of settings, our smartphones and these kind of things are getting integrated. So it's a beast of a chip, pretty big. I mean, so if you look at the area, it's like sort of 250 plus millimeter square. So kind of quite well-sized chip. And then typically in our systems, these chips are placed on printed circuit boards, and those printed circuit boards are then mechanically supported through whatever the packaging of your system. You could sort of compare it against some of the other chips in this thing, and you'd see that it's a pretty hefty thing, but even bigger stuff is getting out there. On the other hand, so that was a one direction, right? Packing lots of power into one. On the other direction, a lot of cool stuff is happening on the tiny end, which is set environments where our interest is in packing functionality in form factors which are super tiny, and we may also be very constrained by power and heat requirements. So Apple's watch, which probably some of you have, is a good example of it, that in a very tiny form factor, there's a lot of stuff being packed together, right? I mean, its processing is not that far off from laptops of less than a decade ago. The memory is amazing, right? I mean, the Apple Watch I have is, I think, 32 gigabyte or 64 gigabyte. It's just it boggles that kind of how much they have packed into it, right? And it has some onboard sort of pretty cool human interaction, graphics, stuff like that going on. Bunch of radio technology, right? Wi-Fi, Bluetooth, talking to satellites, and so on and so forth, cellular and all. So this is the heart of Apple Watch, and again, bunch of chips, right? I mean, so it's a marvel of packaging technology, and then each one of these chips have a lot of different stuff going on. One of the new technologies that has emerged lately is a concept of chiplet, and actually UCLA is playing a very critical role in that. There's an ECE department, there's a center called CHIPS, CHIPS, and their claim to fame is that instead of taking these discrete chips and putting them into a circuit board, and all of that costs a lot of volume and slows things down, they take the bare silicon and then put them on a bigger piece of silicon and really integrates them. A good example of that are, if you have a Apple laptop, for example. So Apple like a couple of years ago, switched to the so-called M series processors, which made a lot of noise. And a lot of their performance and low power comes out of the same kind of advanced packaging of chiplet type thing, where they take chips, put them into silicon directly, and really have them together with very low power, very high efficiency. So that's the other extreme. Another example, which not a few years ago, if you recall, NASA had sent this mission where they had the rover up on Mars, and then it also had a drone that flew for certain distance on Mars and took some pretty cool photos and all, right? And so this is an example where you're kind of operating in an extremely you're operating in a environment which is harsh and I guess also unknown, right? I mean, we're sending something up out there, but one of the things also is that as you go into space, you get exposed to what are essentially radiations which are coming from the cosmos, if you may, and they carry certain kind of particles, if you may, as in energy particles, and they disrupt our digital systems. So when you're designing stuff which is for high altitude or operation in space or operation inside a nuclear reactor or near or whatever in a atom bomb carrying missile and all, you have to make your stuff rad hard. You're on Mars, you're also being subjected to harsh temperature cycles and all. So this is an example where, again, much like the Tesla example, it needs to be super resistant and all, tolerate extreme conditions, errors that sort of result from it. Now, interestingly, what happens in this kind of realm is that when you are designing systems, you want it to be like extremely trustworthy. I mean, every part of it, hardware, software, stuff like that. So oftentimes they use relatively old and mature technologies, which is very well tested, as opposed to cutting edge stuff, latest things which are coming out. So In this particular case, interestingly, the processor which was used was a same processor, a processor from IBM, which Apple used to use when they first introduced iMac almost, what now, 25 years ago, right? So at the time, NASA sent it, let's say 2 decades old, still sort of quite why did they do it? It's not that NASA had a shortage of money. It's really because of this factor of radiation hardness. Okay. In fact, to make things rad hard, as it's called, cost a lot of money. And so I just wanted to point out that not everything in digital systems is about speed, performance, in the sense of how many operations I can do. Oftentimes it's about packing things in a tiny form factor. I gave the Apple Watch example. There's a lot of other cool stuff people are doing, like putting stuff inside brain, putting stuff on retina, stuff like that, right? I mean, really, really super tiny stuff, right? Like, for example, giving vision to sort of people who have lost their eyesight. So they put something on the retina to stimulate the retina. There's a camera outside looking at the scene and then sending electrical signals and essentially giving a few pixels worth of vision, implanting things inside the brain so that people who have memory loss or epilepsy or these kind of things, their brain can be stimulated. So that's another example. The third one is operating in extreme environments, right? Extremes of temperature and extremes of sort of radiation and things like that. Okay, so I guess different people like to work in these different frontiers of digital systems. Of course, in this opening course, we are kind of just going to look at some bread and butter issues, but those of you who are interested in getting into research in these areas, I don't do research in this area, so yeah, I'm not the right person, but UCLA actually happens to be one of the top schools in this space. And also generally, if you've been following news and all, I think in recent past 1 year, America has again kind of started down on bringing semiconductor technology in a big manner in the country. There was a big CHIPS Act, which is like $300–400 billion, and fabs being opened up, and there's a huge shortage of researchers and like really jobs which are coming in. Also, a lot of universities and all are investing a lot, because while money can create whatever the industries, but people are needed to man them. So at least those of you who are consider that as an area. Now, historically, a huge role in where we are has been placed by semiconductor technology. So digital systems have existed for ages, centuries. The very first digital systems were basically made using mechanical gears. Then came gears combined with like motors and relays and stuff like that. And so even until like 1940s, vacuum, the sort of precursor of current modern thing, were relays and valves. The old radio, you may have seen these glass tubes which glow and all, which you see in some old Hollywood movies and all. That's what the technology used to be. Not very scalable. We could have like a bit would mean really kind of a big chunk, okay, not like 64 gigabyte in a tiny chip. In fact, ironically, we are again headed into an era where there's a new technology coming where its counterpart of bit is pretty huge. So that's quantum computing. I'm sure some of you may have heard about it. Professor Jens Palsberg teaches a pretty cool course around it. And if you visit some of these quantum computing labs, they're qubit, as they call it. They're huge, okay, and they're cooled to near absolute zero and all. So there's a lot of fun stuff. That's probably another extreme frontier. But here, I just want to talk about semiconductor technology, which is what the current sort of industry depends on. So semiconductor is any material which has properties of both a conductor and insulator. And it turns out that if you have a material like that, that can be cleverly used to actually act like a software controllable switch. That is, I give it in from software, and then I can turn on the switch or off the switch. I can also use this device as an amplifier. I give it a signal, and it will give out a replica of that signal with more energy. Okay, so these are the two roles. This device, which we can call transistor, which we can make using semiconductor, can be done. So it can amplify or it can switch. Now, for us, switching is more important. If you were in an analog circuit course, it's the amplification which is more important. So the concept of transistor is just about a century old, 1926, by a Polish physicist who kind of conceptualized this thing and actually patented this stuff. But he couldn't build it. And it took another couple of decades before it was built. And it was built by three physicists at this famous lab called Bell Labs. And they sort of made a version of the transistor, which just a short number of years later, they kind of invented in 1947. And in 1956, they had the Nobel Prize because it was pretty cool accomplishment. But this particular transistor that they built was not very practical. Okay, so while it showed, but it wasn't, it's not the one which we find commercially currently. So the commercial version that came up is by one of the same physicists, Nobel laureate William Shockley. It's kind of a year later, and it's called bipolar junction transistor. If any of you are engaged in kind of some hobby electronics and all, you have probably used a BJT transistor. They come under the name of NPN and PNP and all. So a lot of people kind of use it, and it was commercially successful. But even this is still used, but this is not the one which we use in digital systems. In digital systems, we use what is referred to as this final one, metal oxide transistor here. Okay, which actually is the same type of transistor which was originally conceived, but couldn't be built. Again, this was also done at the labs, but like 1959 or so. And this is the type of transistor which probably you learn about, at least those of your EE in your devices courses, which is what is used. Okay, so let's see. Yeah, and these things are made usually, most of the transistors we work with using silicon. Okay, some of them are used using other materials, but mostly silicon. Okay, so that was transistor, 40s and 50s. But there were still discrete parts. Literally, you will buy a transistor, okay, and then it will have 3 pins, and kind of you'll put it into your circuit. Then a second game changer was the idea that we can put many transistors on a flat surface, integrate them, make them in one go. And that idea was first shown by this guy called Jack Kilby from Texas Instruments, one of the very famous companies in electronics out of Dallas. And he showed in 1958, and unfortunately, it wasn't truly totally integrated. It still had some gold wires and all coming out. You kind of see it out here, this thing. But it was the first demonstration, and again, he too got a Nobel Prize in 2000 for this work. Half a year after that, this guy Robert Noyce at a company called Fairchild, which is a very storied company, or it's no more, but was, and he showed the first truly monolithic integrated circuit, very similar to what we use now. So essentially around 1960, he was one of the co-founders of Intel. And I was reading that apparently in 1960s, by far, most of the production of this thing was used by NASA's Apollo program because they were very weight challenged. Kind of the lunar module and stuff like that. So basically, that's where the stuff was being used. Modern IC chips, the ones we use, which you kind of what I was showing, was basically trace their route to Robert Noyce and then the MOSFET transistors. The big win, the reason they have been so successful is the fact that we could integrate them on a single chip, a single piece of silicon, and then how do we make them en masse at scale? So like, you are not making a transistor at a time. You are making all the transistors on a chip in a single go. And what that has translated into is that we can really make huge chips. So you see out here Apple's chip, which is their M2 chip. I think it has 8 billion transistor or something like that. And then here you see a big chip from a company called Cerebrus, which is a company making systems for neural networks. And this thing that this guy is holding in his hand, right, is probably like 6-7 inch by 6-7 inch, is a single chip. Okay, so it's probably the world's largest chip. Okay, and it has trillions of transistors. Okay, so we are at kind of that point. We can routinely, I mean, in your consumer scale devices, Apple is putting, let's say, order of 5 to 10 billion transistors. And so in 40 years or so, for 40 to, let's say, 45 years or so, we have kind of come long way. And that's kind of the magic of this industry, that kind of we've just been on this relentless space. And this stuff is often referred to in terms of so-called scaling laws. So one which I'm sure at least you may have heard of in sort of popular media and all, the so-called law. So Gordon Moore was another co-founder of Intel, the company's processors we use a lot. And he had made an observation that every technology generation, by that I mean that when they move from one way of fabricating to the next more shrunk version, after because I mean he created Intel, so he kind of had the benefit of those observations. He kind of said that every technology generation, the number of transistors they could pack on the same chip, on the same area of silicon, was doubling. Okay, so that's one, and this thing kind of continues even today, although perhaps slowed down a little bit, although it is supposed to, people have been talking about Moore's law will hit a brick wall in, like, originally it was like 2017 or so. Now it's like maybe another 2-3 years. Every time there is speculation of a brick wall, the people who talk about, who make these things come up, have another sort of trick up their sleeve. Fundamental bottleneck is, I have a piece of silicon, how tiny a transistor can I draw on it? And we draw it using lights. In effect, what we do is we create kind of a mask through which we shine light, and that light, when it falls on the piece of silicon, which has some other chemicals on it, results in transistors being formed. So originally the thought was, I cannot draw something finer than the wavelength of that light. Stands to reason. I can't draw something finer than how fine the tip of my pen is. But then through some clever optics and all, they kind of dealt with that. So we are now making transistors which are 3 nanometer, I think. That's the latest technology. So think of what it is, right? The hugely sort of tiny dimensions. A manifestation of this was another scaling law, which really kind of followed as a consequence and some reasoning. So it basically says, roughly speaking, as transistors get smaller, the power density remains the same. So Moore said, if I take a chip, let's say a centimeter by centimeter chip, the transistors on it doubled. What Dennard's scaling says that because of the way things work out, the transistors will double, things will get faster. And by the way, the amount of heat coming out of it remains the same. Amount of power I need to give it remains the same. This part stayed true until, let's say, 15 years ago or so. Now we are on a slightly different curve. Moore's law continues, but Dennard's doesn't. And there's a rationale behind it, which I'll not fully try to explain, but it basically says, Moore's law says every time I shift technology, the area gets half, right? Number of transistors get 2 times. So for the same number of transistors, the area gets half. Then capacitance, those of you still remember your high school physics, capacitance is it depends on area and the distance between the plates of a capacitor. So capacitance changes as the length. And since area is getting halved, that means length is getting 0.7, right? 0.7 times 0.7 is 0.49. So that's roughly half the area. So capacitance is shrinking to 0.7. So then it says to keep the electric field the same, electric field is voltage divided by the distance. So to keep the electric field the same, voltage will have to shrink by 0.7, and then current and the speed of the transistor, same way. Circuit delay therefore becomes 0.7. Therefore, frequency goes up 40%, 1.4 times. So that's my transistors. Those I have twice in half the area. I have the same transistor as now as previous generation, but they are running 40% faster. You add it up, the power, and also the power changes to 0.5. So my area went down 0.5 to 0.5, power went to 0.5, so ratio remains the same. So this was pretty cool because what it said was I can keep shrinking the size of my circuit with the same level of intelligence, if you may. I can keep the speed going up 40%. And by the way, I still have to supply the same amount of power. And I therefore have to remove the same amount of heat. And that was great until 2005-6. So at which point in time that some of these assumptions broke down. And at that point in time, my chip started becoming hotter. Okay. And in fact, so hot that inside of some of these chips are hotter than the nuclear reactor. So what that meant was that I can make big chips, Moore's law still holds, but I cannot keep all those transistors active at the same time. Because if I were to keep them active, right, actually doing computation, then the chip will burn itself out. So if I have, so while I can put more processors, but I cannot have all those processors active, or alternatively, I need to run them at a slower frequency. So this is a problem, what is often called as dark silicon problem. That is, I have to deliberately, while I can build them, I cannot afford to keep them keep them active because so much heat will come that I have no way to sort of deal with that. I cannot take this heat out. Of course, we put cooling technologies and all to help there, but then that in itself takes more energy. So it's a complicated thing, but we are still in an era where at least we can integrate more. So what in the past 10, 15 years, what's happening is that people have begun to say that, look, maybe I can gain efficiency in a different way. I can gain efficiency by designing hardware, designing computers, which are specialized for my application. So, well, luckily for us, something like that emerged, neural networks. Almost everything we are trying to do with neural networks. So there's a lot of activity on hardware for machine learning. Essentially, that big chip I was showing from Cerebrus is an example of that. And even on Tesla's chip and Apple's chips, you see big parts are these neural processing engines. So these are examples of recouping some of that loss of Benard scaling by making our hardware specialized. So no more Intel x86 processor sitting there, jack of all trades, too inefficient. We start putting specialized processors. And that's the era we are in now. These are often called as domain-specific computers. In fact, the CS department here, Professor Jason Kong, has a center called Center of Domain-Specific Computing, which is really focused on that. So it's a huge area of opportunity and activity right now on how can we efficiently create hardware for custom applications and still have them be as easy to use and program as our general purpose computers are. And so a lot of people who do research in this space and all these other kind of things they are kind of addressing. In fact, Ji Cheng's work is solidly in kind of that territory. So he's a great person to kind of give you more insight into that. Okay, so that's where we are there. So now let's see. We are kind of at a halfway point. So I'm sure you are pretty bored with listening to me. So let's take a 3-4 minute break before we resume. And meanwhile, come and talk to me. If nothing else, introduce me. If we have any questions, I'll happily answer them. So let's see, it's like 2 minutes to the hour. So let's say we start at 3 minutes plus the hour.
Last time, 550 or 650.
It's at 550.
It's like the first slide is 7.
Oh, did it?
Yeah.
Sorry.
I had another class, like, at this point, I think like 10 minutes late. I just wanted to know where you
I was probably just setting up my this slide, but I thought I had when you see.
And then are you a
Slides around. Yeah, it comes up to that.
Do you think we on the customer? Do you require us to be like to resolve the? So I guess we can leave or we say more about that too.
You can leave. That's fine.
Okay, well, I guess then there's something.
Yeah. All I would like you to do is that one of you should just come at the start of every class, just in case I have some heavy issues.
I'm sorry, Professor, maybe I could not attend for Wednesday, or I have the 4-9.
I can.
Yeah.
You can do it for Wednesday. Okay, I can do it for Monday.
Okay. Well,
You do not need to make it 4-9. We have a.
I already. Okay, yeah. Okay. Well,
So how could we set up this? Yes. That's why.
I don't think.
Oh, hi. That's the one. You can just call me money. Any? The film, we don't have I'll actually, it's on going. I'll post it. Oh, okay, yeah, I must have overwritten it. I'll fix it. Can you make a posting on Piazza? About it? Okay.
I just wanted to ask for clarification. So Moore's law is only really, it's still applying for integrated circuits and stuff that are being specialized now, right?
So, no, the Moore's law is just about the number of modules.
Okay, so.
Okay,
just for-
so we can still build a transistor. That's not an issue, because that purely has to do with our ability to actually just put transistors on silicon, and advances in optical size have taken care of that. It's costly, but we can do it. The problem is coming on making sure that we have a good what is referred to as yield, that is okay, let's restart. So one student pointed out that the link to the lecture slide says that it's in my trash out there. I was updating the slide, so it's probably happened as a result. So I'll fix that. And also, I thought I had put the syllabus link, but evidently it's not on Piazza, so fix that also. So just those two things. And then finally, there was a question out here. Yeah, so again, just to make it clear, Moore's law is still kind of working, perhaps maybe at a slower pace, in the sense that we are able to keep shrinking the technology, right? I mean, we have been moving from 7 nanometer to 4 nanometer to 3 nanometer and so on and so forth. So that's been happening. But just because we can put more transistors in a given area doesn't mean we are able to use them. And that's where the challenge is coming, that we can't keep active all the transistors we are able to put. Our ability to put the transistors there comes from our ability to fabricate, manufacture, and that has been driven by some pretty cool advances in the optical side of things, right? The way we draw transistors using light. They've been very expensive. Semiconductor fab takes maybe order of 10 to $20 billion to make, so it's a pretty expensive factory and requires some very specialized talent, people with PhD degrees in physics and EE and all, to even sort of create a next generation process, material scientists and all. But it's been happening. The challenge is coming from that we just can't run them without slowing them down. So a lot of growth in terms of we were making things smaller and gaining in performance support linearly, that has kind of disappeared. Okay, so now let's look at the logic design part of it. So, so logic design refers really is how do we think about implementing the computation that these systems have to do. And essentially, we in engineering in some level is about making complex systems from simpler components, and then those simpler components from yet other simpler components, right? I mean, whatever system, whether it's a ship or a space shuttle or a brig and all, that's how we kind of make these things. No different out here. How do we make complex digital systems from simpler primitives? And the simplest primitive, of course, is a transistor, but transistor is kind of like an analog beast, right? I mean, it in itself doesn't have any digital behavior, although it can act as a switch. And that fact that I can have a conceptually you can think of as transistor has 3 terminals. One other terminal, if I give it a high voltage, then it connects the other 2 terminals so the current can flow. And if I give it a low voltage, then those 2 terminals are disconnected. So it's literally like a switch, wall switch, except instead of you switching, someone is sending it a 0 or a 1 to switch. So it's kind of a programmable switch. Okay, so that kind of gives it's very similar to what used to be relays. Even now, like if in many places like your HVAC system or your pool system, you'll find relays which are made using a solenoid with a mechanical thing, and then you supply AC current and the solenoid charges up, and then the mechanical thing moves and the switch closes. That's how, if we are switching very large amount of currents, like in a pool motor, that's what we do, right? So we work with relays there. Okay, semiconductor technology is kind of getting there, but not still very good at if you're switching huge amounts of current. So that's so those relays are often called as contactors. But if you're working in this digital thing, you're just moving information around. Our purpose is not to move energy around. In that case, we can work with transistors. They act as relays. They are moving around information. And that part, that transistors can be used to implement programmable switches, which can then be used as a foundation, as a building block of digital systems, is what actually in 1930s, very famous person called Shannon, his master's thesis at MIT, basically kind of laid out that how we can design digital systems in terms of using this kind of a logic, these building things. Why is Shannon famous? Anyone else? Besides this? This was actually not his famous work. Yeah. Information theory, yeah. Shannon's information theory, kind of cool stuff. A lot of EE and a lot of CS. And interestingly, he was at the same place where the transistor was. So all of these people were sitting in that one lab. Okay, so going back out here, primitives for building digital systems are kind of basically two things. Logic gates, essentially, you can think of them as very simple mathematical functions, which do some operations, Boolean operations, very similar to like in programming languages when you have and or and not those kind of functions, some super simple functions. And state machines are, again, if you are a computer scientist and if you have done a course on automata theory, so you may have learned about finite state machines. Okay, so state machines are basically abstractions of something which is happening in steps, computation which is running in steps. So you can think of computation broadly really has two elements to it, right? How do we step through a sequence, right? Take branches, right? Based upon some information, decide to do this or that, And the other thing is the actual function, addition and ending, and right. I mean, these when you write code, that's what goes on. So digital systems essentially have these two kind of things: logic gates and the state machines. And then using these building blocks, this part is often referred to as sequential. Okay, so it's basically saying that this is what we sort of, it helps sequence the operations, and logic gates are the actual operations. Okay, they are often, the logic gates are often referred to as combinations. So sequential and combinational are kind of the two parts to it. So the whole process of design then is given these building blocks, can I take my algorithm and implement it in hardware, or maybe hardware and software? Software is nothing but an algorithm running on hardware, on the hardware which we call as processor, right? So there are two ways of implementing our concept, our algorithm, our specification. One is I map it directly into hardware, and the other is I map it to instructions of a processor, which in turn is built within hardware. Okay, so kind of idea behind courses like these is to kind of really give you both a practical perspective, how do you build these things, but also a principled approach, right? Because our systems are so complex that we don't want people to be just hacking their way through. When you design these things, you need to design so that you can talk about it's correct, when will it fail, what are its limits, stuff like that. And also the first principles understanding is very important. So it really has two elements to it. There's kind of a nice little quote from Elon Musk, which I kind of like, but which is, faced with a complex system, you kind of try to break it down into the pieces and then you kind of reassemble it back up again. So hopefully, so a lot of kind of the mathematical machinery which we need to design digital systems in a good manner. So hopefully sort of will convey that. And that's important, that when you do problem sets and design assignments and all, I'm not just looking for a design that works. I'm looking for a design that is elegant, okay, which is which adopts good design practices and not just hacking our way through. Okay, and the reason is because if you hack your way through and all, might work for kind of a course problem set, but it fail miserably when you scale things up. And what we will not learn about are some of the things that I spent in the earlier slide. We will not talk about how we make these gates using transistors. We will not talk about how we fabricate these chips and silicon. We will not talk about the software that runs on these digital systems. There are, of course, other courses that kind of do that. We'll limit ourselves to, given a specification and an algorithm, let's say, given a specification, select an algorithm and then figure out how to implement that algorithm using these gates. Okay, that's kind of the idea. An alternative way of doing like this would be, given a specification, you come up with an algorithm and then write code for it. That you do in CS 31, 32, 33. We are not going to do that. We are going to focus on how to implement that algorithm using gates. And of course, the kind of algorithms we can work with in hardware tend to be a lot simpler than the kind of algorithms you will work with in software. So logic gates and state machines are kind of our building blocks. At some level, they are useful whether you are mapping to hardware or whether you are mapping to software. So even in software, oftentimes we design things in terms of finite state machine. And of course, we use Boolean operations. So no different out there. It's just that software is the building blocks in case of software are the instructions that a processor provides, whereas the building blocks for us is a library of hardware units that we'll give to you. So implementation to hardware really differs at the back end. The first few layers of the thinking and all is very similar. The specification, you derive an algorithm, you figure out what would be a good algorithm for problem at hand with the constraints that we have, and then work with this. There's a couple of different things. Hardware is different in the sense that instead of a processor and things running in lockstep on it, here we often have to worry about like lots of things happening in parallel. So it's a very different mindset. The second thing is timing plays a very important role in hardware. When is what happening in what sequence? When you are doing your software courses, I'm sure all of you have probably done CS31, some of you may have done CS32. When you work on programming, you kind of largely focus on take this data, put it, create some output in a file, or print something, or draw something on the screen. Timing and power and these kind of things don't matter much, if at all. Whereas in hardware, they're front and center. The same output produced at the wrong time is incorrect. Okay, so one has to be super careful. And in fact, you will see as we proceed, a lot of my specifications would talk like in the design part of the course, they'll give you specification on the timing behavior of the system you're designing. And that's how these systems are. You have to make sure that not only you are creating the correct value at some point in time, that's not the idea. You have to produce the correct value at the right point in time. And if either one of those two things fail, if, in the sense that if you produce the correct value at the wrong time, it's wrong. And of course, if you create the wrong value at the designated time, then it's wrong also. So hardware is different in that regard. We'll talk a lot about along the way on what makes for a good digital system design. Functionality could be implemented in hardware alone, could be implemented in software alone, and a combination of the two. In this course, largely we'll focus on hardware alone. So that's kind of the idea. Software, we are kind of used to a much more relaxed process. We write some quick and dirty code, run it. If it works, yay. If not, we go to Stack Overflow, put something in there, try again, iterate, debug until it works. Companies do the same thing. They put out alpha release, beta release, try it, they get bug reports, they fix it. Hardware, we can't do that. Intel can't iterate on processors in that manner. So hardware requires a more disciplined approach to design, where as much as possible, when pieces come together in a large international team, in many cases, then when things are put together, it ought to work. You don't really, iterations are very costly, time consuming, and take a lot of cost. So, okay, so we'll talk about sort of principles of what are good design. My hope is to really kind of drill those things in. How do we represent things in a digital system? How do we make designs which are modular, as in little subsystems which cleanly connect together? How do we think of a design hierarchically, optimizing for speed, optimizing for other aspects? How do we improve performance? So that's parallelism and pipelining, two key concepts which we'll do very much at the end of the course. And how do we, and this is not something we do manually anymore. Okay, these things are way too complex. So there are design tools, just like on software, you have compilers. Likewise, on hardware side, you have compilers, or what is called as electronic design automation tools. So we are going to see some of those along the way. Okay. So now to some logistical parts. There is a textbook. I put it as a recommended thing. Honestly speaking, if you are comfortable working with the slides, then really no need to buy it. Probably its only value is the problems which exist at the back, but even there, I do not just copy problems from textbooks. So they're good for practice, but honestly, I'm sure you can find similar problems from a lot of web resources. The only reason I'm saying this thing is I feel textbooks are criminally priced, so I don't want you to buy them, but it's your money. So um, lectures draw upon obviously some material from this book and a lot of material from other places. I keep revising them every year and all. This book never came out with any further edition, so it has some typos and errors, so be a little bit careful. So anyway, that's the book. The course does follow the book in the sense that the different modules I have do correspond to the chapter headings that this thing has. So even though the final material has changed, but sort of kind of listed that thing. I'm sure maybe you can find some way of accessing the book. There are other resources on the web. There is this textbook at Circuitverse, which I think is pretty decent. There are obviously Wikipedia, and of course, nowadays you can always go and consult ChatGPT and these kind of tools. Okay, as long as you know whether they are right or wrong, and so that onus is on you, but they exist. Online presence for the course. There is Brewing Learn, which is kind of the official entry point, but then from there you can get into Piazza and all. The only thing I have posted on Brewing Learn is basically the course syllabus. I don't intend to use anything from there. It's a very clunky system. So I use UCLA Ascension tools like Piazza. All the course material you will find there. I generally post the videos on YouTube. Video is one thing that I do like to post on Brewing Learn, but because it has this auto captioning feature, but so does YouTube. When you are playing a video on YouTube, you can kind of have it play back the captions for you. Okay, so I think technology has advanced quite a bit. More on Piazza. So yeah, okay. So what else? Email, I have repeatedly said, is not a good way to reach me or the TAs. So try to use Piazza, but if you want, you can. We are going to use Gradescope. Hopefully you have encountered Gradescope. Again, it's another UCLA sanctioned thing. I'm not using anything which is not officially approved by UCLA. So just want to put you at ease in terms of any privacy considerations. Gradescope allows online problem sets, online quizzes, as well as auto grading capabilities. In this course, we do rely quite a bit on auto grading capabilities. So Gradescope we use quite a bit. You must log in using your UCLA credentials. Both Piazza and Gradescope, they are configured so that they get they sync with the registrar roster, and which means that the emails that they use are the ones which are on your registrar records. So if you have a private Gradescope account or a private Piazza account, you will not be in there. Now, unfortunately, on Piazza, I have no way of adding any external user. So if you go through Brewing Learn and go to Piazza link there, you would get to the right Piazza. So this just makes sure that. And Gradescope is the same story. For a variety of reasons, I will not entertain any private Gradescope accounts. It has to be your official one. Okay. Gradescope's auto grader. So when we do quizzes and online PSETs, basically things which are kind of fixed format answers or multiple choice and all, they get auto graded. So that's how we configure them. And then there are some questions which require you to do a free-form answer, which we grade. For design assignments, you create designs using a tool, and then we grade them using simulation-based auto-grader approach. The reason I mentioned this thing is the following, that it's very important to stick with the required specification on the format of the answer. Okay, because if you don't, then you'll get a 0 score and it will stay 0. Okay, we can't, for large classes like this, we just can't go around and look at all those weird formats. We don't, I mean, the scaling of grading is unfortunately an issue. So please pay attention to it. If we have to grade manually, we do it, but then there is kind of a significant penalty that we put on that. Okay, so please don't test that. Grading schema. So this is probably the one which you are most interested in. Problem sets, these are basically conceptual things, 2 to 3, usually 2, sometimes 3, may require use of software tools in the process of doing it. Not write software, but making use of software tools. Design assignments, again, 2 to 3, usually, I think last year I gave 2, this thing is 3, will require use of software tools because you're going to create a digital system, simulate it, and then you're going to submit, and then in the automated case, we are going to subject to some tests, and again, you can do it, as well as a written report of some form that we will ask for. Quizzes, 2 to 3, usually, again, I've done 2, maybe I'll do 3. There's a quiz in the last lecture of the quarter. We can think of it that as serving the purpose of the conceptual part of a final. So that quiz we know for sure. One more quiz I'll probably have on the week of May 8th. That's a Monday. So May 8th. Yeah, that week is where I'm targeting, and there might be a third quiz. Okay. Take home final. This is design oriented. Except those of you who are honor students, I'm sort of giving you an option of doing a research project instead. So if you're enrolled in 89, you have an option out here. And then finally, discussion section and participation, we give points there. So every discussion section has kind of an associated activity, and you are supposed to do it. We kind of grade it more liberally in the sense that it's more about doing it as opposed to forcing you to do it, so that you sort of keep up with the course. Participation is your participation on Piazza and office hours. We track these and we assign scores based on that. On this final part, discussion and Piazza, I've kind of given some more details, but essentially, you can be active on Piazza either by asking good questions, not random stuff, and likewise answering questions. Okay, so, and Piazza has tools by which I can easily collect statistics and all. Usually I found the students who are actually active on Piazza would probably be getting an A anyway, because oftentimes I've also seen that students who were otherwise struggling by taking part, they actually improve quite a bit. So I think that discussion generally helps. And likewise, going to office hours, if you are attending an office hour on Zoom, then just in the chat window, just type your name, and so that we know that you that way we can have a log of that. Okay. Let's see what else. Assignment of grade. So I'm not going to walk you through this thing, but this is what I basically do. For every individual assignment, we first just grade it as whatever comes out, right? I mean, as we're grading. Then if the median is lower than 80, then we readjust the score so that the median on that assignment becomes 80. And the highest score on that assignment becomes 100. We do a linear scaling on it, except if you got a 0. If you got a 0, it will remain a 0, because otherwise we don't, you got a 0, like for example, maybe you didn't even take the test. We don't want you to get a score then. So if you have a 0, it remains a 0, but otherwise, so if the median is already higher than 80, it remains higher than 80, we do nothing. But if it's lower than 80, we make the median 80, that's one constraint, and the highest score becomes 100. That's the second constraint. We fit a line, everyone's score gets adjusted unless the score was already 0. And then we do it, we assemble these things across the course. So remember, this thing is being done at an individual level. And then this is the final schema. If the score is in 90s for the course, you will get some sort of an A minus, A, or A plus. Likewise, the scores is in the 80s, you get some sort of a B, and if it's the 70s, some sort of a C, and 60, some sort of a D, and below that is a A. A grade of C or better is required to earn a P in case you are taking on a pass no pass basis. So this is how we kind of do this thing. We tend to have, depending on the year, lots of A's and lots of A pluses also, but also lots of people sitting around here also. So it's almost like a bimodal kind of a distribution, which often emerges. Anyway, that's what we do. So the reason I do it this way is because oftentimes I misjudge the difficulty of a problem. Okay. And in which case, so I don't want to say, oh, okay, everyone flunked or everyone got a 60 and all, because remember, it gets normalized. Okay. So the median will always be at least 80. Okay. So that's, and oh, the other thing is when we are doing this adjustment, if there is any extra credit, we set it aside. So we do this adjustment on without the extra credit, and then we just put back the extra credit. So again, the intent is sort of always be on your side as we are doing this normalization. Okay, so if, like I said, if the median is already higher than 80, then you benefit. Okay. Okay, any questions? Okay, let's see. So I guess, yeah, this is just a pep talk. I would really say that, look, keep the focus on the learning part. I mean, I think every professor says that. I know it's hard as a student. One thing which comes up is we are not going to override or make exceptions and all in terms of when it comes to things like auto grading and all. So we design it so that there are a large number of tests. If your design is failing on most of the tests, there is something seriously wrong anyway. Okay, so unfortunately, much like in many of the software courses and all, right, subject to the test, there's no partial credit at that level. And it's very hard for us to meaningfully assign partial credits. So we give you ability to test. We expect you to design tests. Okay. That's a key part of our design, right? Design doesn't end by just writing down some equation or circuit and all. It ends when you have confidence that it will work. So we want you to go through that process. So the reason I'm saying all of this thing is that you may find the notion of auto grading harsh, and I can understand that. But for design problems, there really is no other meaningful way out, because these are complicated design problems, and you need to get used to the idea that in real life also, your customer will not care if your system, the car crashes, and you'll say, but I put in the effort or this thing, right? I mean, tests matter. So we'll throw in lots of tests and statistically across them. What we do is in the autograder, we have designed things so that I can give you feedback as to what happened, why did it fail. Hopefully, sort of that provides you some insight into that. So anyway, that's the comment out here. Late submission, that's the other thing which comes up quite a bit. So late submission policy, I'm going to just scroll through rapidly. Okay, so you will have a budget of 8 calendar days for the quarter. You are responsible for tracking them. We will have no way to let you know how many late days you have used at any given point in time. We just tabulate at the end. If you exceeded 8, then we are going to discard the rest. You can use them towards problem sets and design assignments. You cannot use them for quizzes or for the final. You must use them before the Monday of the finals week. So like, for example, let's say a piece set was due Friday of the last week of classes. So you can say, hey, I want to now take thing of the Monday of the finals week. That's not allowed. You have to finish it by Sundays. Late days, no more than 3 late days can be used towards any one submission. We really need to move on with the grading, and so we have to cap on how much delay you can have. Late days are used in chunks of 24 hours. So if you are late by an hour, well, you have lost the whole 24 hours. Make sure of any last minute internet snafu. That burden is yours, not ours, unless there is an outage which affects humanity or great scope at large. We'll do with that, and use the late days judiciously. I think the biggest problem I have seen is that students in many cases end up using late days early on when actually the assignments are simpler, but they just have social obligations and all. And then when later on there are assignments in the later parts of the course where you really need it, they struggle. Unfortunately, we won't give any extra late days. There is just one exception to this rule, which is if you are eligible for any special accommodation officially sanctioned by the campus, and they ask me to give you additional days. Okay, that would be the only exception. Some students are in that state. If you are, you can get in touch with me, have your counselor contact me, but there will be no sort of 8 days. I feel is plenty for a course like this, given that we'll have 4 to 5 assignments. So you're essentially getting roughly 2 to 8 days per. Okay, the other issue, want to spend some time. Last year in a class of 95, I had 10 cases of honor code violation, and they were all penalized. And I detected, I'm sure I perhaps I missed some others, but one of the benefits of using AutoGrader is that we are very good at detecting cheating cases. Don't test us because we will detect you. Okay, so well, you can take it as a challenge perhaps, but it's too much of a risk for you, particularly at early stages. Okay, so what is permissible? Firstly, with ChatGPT and all in the news, you are welcome to use it. Quite likely it will give you wrong answers. In fact, I will design questions where they will some questions where it will not. I'm not going to penalize. You can, in the sense, you can use these tools. Okay, in fact, I encourage you to use these tools. I think in future, the best designers would be the one who effectively use the tools. So learn how to use, but learn also how to when to trust them and when not to trust them. So you can use any software tools and all. What you are not allowed to do, number one, you are not allowed to use any sort of service which does assignment on your behalf. I know such services exist. They contact us, and this is one of those fireable offense kind of a thing. If we catch you, you'll be suspended. Okay, I mean, I can assure you of that. So don't attempt that route. The other thing is, yes, what can you collaborate on with your peers in the class versus not? So this is a general guidance. It's okay to discuss what does the question mean. It's okay to discuss which lecture would it correspond to. It's never okay to share your answers. We have these cases where a person flashes their design on the screen and then claim that the other student just did a screen capture and then replicated the design. Both of you are equally guilty. So thou shalt not share your answers or designs in any shape and form with anyone else in the class. So collaboration ends and discuss. Unless, again, this applies to certain things where I may allow collaboration explicitly. Okay, but other than that, please don't, because what happens is that usually you'll make some mistake, and the weird mistakes tell us the social network. Last year, we caught a social network of around 7 to 8 students who were all cheating among each other, and we had just discovered kind of links in that social network. We are good at catching. Okay, so again, please don't. That's the advice I can give, because we will report each and every case. Rest you can read. You can ask me. Let's see what else. Okay, yeah. So this week, as you go to the discussion section, please take your laptop. The Julian sent a mail there. We are using this tool called Logisim Evolutions. Please install it. I also did a follow-up on PRSA. So I use a Mac. So unfortunately, I can give you instructions more easily for a Mac. If you are using Windows, you can just follow the instructions on the main Logisim Evolution website. I would urge you to install it on your laptop before you go to the discussion section, so that you're not struggling and wasting time there. Logisim Evolution is a Java-based program, so your laptop needs to have Java installed. Mac come with Java installed, or it's very easy to install Java. I don't know about Windows. And you need to install the latest version of Logisim, which is version 3.8. There are some videos on YouTube. It's a very commonly used tool at many universities. So if you Google, you'll find things. GitHub is where the code resides. Those of you who don't know GitHub is where open source code and all people post them. So Logisim Evolution resides there. They have very good instructions, but for Mac, I thoroughly encourage to follow my instructions because I think they're easier than what they have there. So work with that. And then let's see. Just a sec. Clock here is wrong. Okay, so the course content now. Actually, before I move on, so any questions on any of grading, cheating, collaboration allowed to, yeah.
So like when I do a final submission, will submit like a script or something that generates the final, like what's the submission?
Also, you upload the file to Gradescope, and then what it does is it runs some tests. Usually the way I configure so you would submit your design file from Logisim, you bundle them up into a zip file and upload the zip file. And then at the back end, I have something called a Docker container. Some of you might know of it, but basically it runs some test cases. During submission period, I configure it so that you can see how your design is doing on a small set of test cases, but not the full set of test cases. Then after the submission is done, we kind of grade it on how you did on the test cases. Usually we also look at, like usually I would also put constraints like you can use this or not that, so we check for those. Like if you use something not allowed, your design is considered wrong. Or we also look at performance, how much time it takes to run, and also we automated measures those things and then spits out a detailed log which I can see, but it gives out a summary to you, and then you can always contact me for a more detailed log. Okay.
Can I like my test cases?
Oh, absolutely. We thoroughly encourage you to, and in fact, in every year, that's one place you can share things. You can share test cases among yourselves. You can even, actually, one student last year wrote a program to generate the test cases, and that was super useful. Okay, so absolutely, you not only you can it's not the question can you write, you absolutely have to write, otherwise you won't be able to do the more complicated stuff. Yeah, you can submit things multiple times. I don't put a limit on that.
When you send the student wrote a program that plays such cases, how does that?
Or basically he wrote a program to generate test cases in the format that Logisim likes to have. So Logisim takes test cases in a particular file format, and also basically he wrote a program which, given the mathematical function that you were supposed to implement, the functionality would generate cases. And also Logisim has the necessary tooling to do testing. Okay, but it requires things in a particular format, so it kind of goes for that. Not a compiler, it's nothing as fancy as a compiler, but that one I'll put a link to it anyway. I think he had shared it with me, so I'll share it with everyone for whatever it's worth. Yeah. Okay. Any other question? Okay.
So like you said, like in this class we'll be writing algorithms, including algorithm. So is that released in some sense to another compiler does to like
It's kind of a similar thing, except that in our case we are not using for going from the step from algorithm to logic, we are not using a compiler. It's you who's doing it in this case. Okay. You can use a compiler because I'm letting you use any tool. So you can feel free to ask ChatGPT to generate things. I tried. ChatGPT is pretty decent at generating Verilog code. So those students who are in the honor section, they are going to be exposed to a programming language which is used for hardware design. I have not tried ChatGPT creating something for Logisim, but I can certainly imagine with some proper prompting and all you could. Okay. And then there is, yeah, you can try other ways also potentially. So, I mean, yeah. So again, feel free to use any software too. That's if you can figure out how to use these things, yeah, achieve the purpose of being a good engineer, right? I mean, I don't want to torture you with manually doing things, but I want you to do the work yourself, not just copy someone else's design, which is where we kind of solidly draw the line. Okay, so. Any other question? Okay, last one.
Is there a program that can actually convert these algorithms or shut them down into the Google model?
Absolutely. In fact, that's how in the industry works. So if you, one thing you can do is you can learn a language like Verilog, where you can write your algorithm and then have it generate the logic gate representation and then manually write it into logic. And then once given that, you can, there's a manual transcription thing, or maybe you can write a piece of code which can write it into logic. So you could. Yeah.
Okay, let's do that for this part.
You can do it. Yeah. Anything, any piece of software you wish to write or find somewhere and use is okay with me. Okay. Again, what is not okay is to assist each other in actually doing the problem. I want each one of you to do the problem yourself. Okay, if it comes to writing code, write the code yourself. If you want to widely distribute the code, something that you wrote, be my guest, post on Piazza. There's no final exam. Quizzes, you won't have time. You can use them. I will not stop you, but you won't have time. So one other thing also is quizzes and all are going to be fast-paced, partly because, again, we notice patterns of cheating in quizzes. Yeah, so I'm already thinking of ways to stop that and detect those. So one of the strategies is that we make them fast-paced so that you don't have time to cheat. Okay, so because yeah, so this but statistically it will again even out. Yeah.
So this is sort of kind of big, but is it like one of those quizzes where you have them from this sort of thing, or is it like one of those quizzes where they have
I mean, always a tale of students who finish it comfortably. Okay. But I basically want to minimize this notion of people connecting on Discord to exchange answers, which we saw last time. Okay. So, okay, so basically the course has kind of 3 parts. Initially, we are going to talk about how to represent and process digital information and the mathematical theory behind digital logic, which is the Boolean logic. How are we doing on time? I have 6 minutes. Okay. So, so Boolean algebra is kind of a logic, the mathematical framework behind this. We're going to spend time on that. This you can say is kind of like the data structures equivalent of hardware. Okay. The second part is how do we create functions in digital logic using building blocks? What are those building blocks? How do we make them? So this is where logic functions and state machines come into play. And then we get into more complicated things. How do we work at a system level? How do we optimize performance and all? So roughly kind of you can say it's like most of the time we'll go into the first in the middle portion, I would say, and the last part, the first part is relatively slow. Okay, and I guess if you're generally inclined towards architecture and digital systems and stuff like that, then M16 is really kind of NCS51A. It's kind of a start of really a sequence of courses that UCLA offers. So there is the digital design lab, there is embedded system focused course. I teach a grad version of embedded system 2, computer architecture, digital design project in CS, digital circuits in EE, and many other courses that exist. Okay, and there are there's just lots and lots of interesting choices that exist. And of course, you're welcome to try out some grad course also. So what should you do in the short run? Download and install Logisim, play with. There are videos and all which can help you. Verify that you are able to access Piazza. If you haven't, do it. Remember, we also know that you haven't accessed Piazza. Okay, I mean, these are things that we can monitor. Every quarter, there are some students, I kid you not, they have not logged on to Piazza until like the 9th or 10th week. Okay, it doesn't bode well. And they're usually the students who are actually already not doing well. I mean, they're basically disengaged. Verify that you are actually able to get onto Gradescope. Again, you may have to go through Brew and Learn the first time to do it. You have to use the single sign-on UCLA SSO. Slides, if you like, you can download and print slides prior to each class. I have already put all the slides out there. Having said that, they are last year's slides. So I am probably going to keep refining them a little bit along the way. So probably a safe time to download slides is the day of, but they're going to be pretty close. I don't expect the content in this course doesn't change in 12 months in terms of industry trends. Slide annotations. I noticed the way I'm annotating today, they are these disappearing annotations. So they're only in the video, they're not in the slides. I'll try to figure out how to get more persistent annotations. if you have a textbook, you might want to read through it. I also have already put the link to last year's and the years before YouTube videos. So you can always look at them if you wish for whatever reason. Again, I don't expect the content to change significantly. It's kind of in a similar style. Again, every offering is somewhat different. So yeah. And I guess the only other thing I would say is this course unfortunately packs a lot of content. Usually in semester system schools, they give a whole semester to a digital logic course. We give only a quarter, and we are expected to teach basically the same thing. It's fast paced. If you fall behind, it's very hard to kind of recover. So don't fall behind, I guess. And get out help, come and talk to me. And all. It may sound that, oh, initially the things are slow paced, I can afford to catch up. We move very rapidly. Okay, so, and again, don't use your late days early on. You will, I can assure you, it will cause misery at the end of the quarter. Okay, so keep your late days maximum allowed to the extent. And then I realize that personal affairs and all may come in the way, but that's kind of a general advice. Okay, great. So any questions before we start? Okay, you go first.
Will you teach Verilog or?
We will not cover Verilog in the main course. In the honor section, yes. They're on Piazza. It's just that the current link is broken. So, so you go to resources and then again go on the resources. Yeah. But the link for lecture 1 is broken. So.
Will the slides from today be posted on Canva?
Yeah, they were actually already posted, but it's just that the link is broken. So I need to fix it. But yeah.
I just have to introduce myself. My name is Marshall.
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 Yeah. Okay. Hi. Good meeting you. You have what? CSE.
Computer engineering.
Computer engineering. Okay. Cool.
So nice to meet you.
Likewise.
Nice to meet you.
Yeah.
Kind of.
Actually, give me a sec. I just want to stop Zoom.